Hi, my name is Sabrina Carrillo, and today I'm going to be presenting on artificial neural networks and how they're being implemented in the artificial intelligence community to help with deep learning and image recognition. So first of all, we're going to provide some problems. So the artificial intelligence biggest problem is trying to mimic the way that humans act, how they think, and how they behave. And with a neural network, the biggest problem is trying to emulate the way that the brain actually learns. So the way that the brain learns is that it has nerve cells, and then these nerve cells fire electrical pulses, and these pulses are called neurotransmitters, and the neurotransmitters communicate from nerve cell to nerve cell, and that is essentially a short synopsis on how learning works in the brain. And now a neural network tries to follow this similar pattern, and it actually is quite difficult to recognize images. Although they're being implemented in the field to help with image recognition, it is not totally accurate, and there are a lot of problems such as adversarial images and adversarial attacks. And so an adversarial image is an image that looks just like another image to the human eye. So for example, here both of these look like pigs to us, but when you run it through, the neural network actually predicts that it's something else. So for example, this first run right here, the neural network predicted that it was a pig. And now what an adversarial image is just another image that has had a few pixel mutations, but enough to where they still look similar. So here we have some pixel mutations, and then when it is run through the neural network again, the network predicts that is an airliner. So these images are the biggest challenge for neural networks because scientists are trying to find ways to minimize this error and be able to have the network predict these patterns more accurately. And so neural networks, as I mentioned before, they try to mimic the way that the brain learns. So for example, how I was stating that the nerve cells are communicating amongst themselves with the neurotransmitters, and they have a dense network and web of all these fire pulses. This is how a neural network works. So for example, a simple example that I can give is a black and white image. A black and white image is made up of pixels, and each pixel has a grayscale value that when you put them all together, it can make the picture. And so a neural network will break down this image and take each individual pixel and take this grayscale value and store it in something called a neuron. So essentially an image is a big matrix of a bunch of numerical values or grayscale values, or perhaps RGB or red, green, and blue values if it was a colorful image. And these neurons are then taken through the neural network, and they run through various layers, and they're put through various mathematical computations. And essentially at the very end, a network will be able to see patterns within and be able to recognize. So this pattern makes up this image, and when you run another image, it will look for similar patterns and classify that image as well. And so essentially the more images you run through the network, that is how the network learns. And this is deep learning. And then essentially the goal is to be able to put any image through the network and have it predict what it is. So currently convolutional neural networks are being applied to this field, and they are becoming quite successful in the image recognition. There are four main parts to the network, and that is the convolution, nonlinearity, pooling, and classification. And so just to explain, the convolution step of running the image through the network is breaking down the image and then creating what is called a filter or a convolved feature. And so this is condensing down the image so that it is easier to run through the network, and it leaves less room for error because it minimizes the amount of patterns that can reoccur with another image. And this is done through taking the dot product of certain sections of the image. So the filter will run through the entire image. For example, here you can see the yellow part is taking the dot product of that specific square and inputting it here. So it creates another smaller matrix. And then this convolved feature goes through the nonlinearity step. And this step is transforming all linear values into nonlinear values, as this section right here the first convolution section, is actually done through linear algebraic equations. And so the nonlinearity section transforms everything to nonlinear values. And for example, it will take negative values and turn those into zeros. And then from there it goes to pooling, which is another step to further complicate the matrices and ensure that there is less amount of patterns that are repeated. And this pooling step is taking, again, chunks of the matrices and putting them into another matrix by using, for example, the sum, the max, or the average. So here in this image, it is an example of a max pooling method, where it's taking the section. So for example, this pink section, the max value is 6. And from there, that 6 is stored in another matrix. And then from there, that smaller matrix goes through classification through its patterns, and it is run through the dense networks. And this leaves less room for error because you're taking the big image that has lots of possibilities for matching perhaps another image, especially since they're all in black and white values or colorful values. And it turns it into a more complex version that has patterns made up from mathematical operations and linear algebraic operations. And now this field has a lot of applications. For example, the forensics community is currently using this image recognition tool for taking, for example, footage or terrorist images and running them through the network to be able to get any important information, such as the location of where that image or video is, or for example, see if they can find out the identity of a person within the image or video. And it is very important to combat these adversarial attacks because actually the wrongdoers or the illegal doers themselves are actually finding ways to mutate images that are released, or for example, hacking into systems and doing that same adversarial attack and mutating the images with a few pixels, or just so that the actual person themselves doesn't know, but when it runs through the network, it completely skews the results. So that is also why it is very important to keep going into these neural networks and trying to combat these adversarial attacks. And finally, also self-driving cars. So for example, the brand Tesla is very famous for this. They have been pretty successful with their autonomous driving mode of their automobiles. And here we have a picture where the car is detecting other vehicles on the road and also detecting the side markers so that it stays within its own lane. And this is especially crucial because now this technology is being applied to actual human lives. So for an error to occur, it could actually result in injury of another human being. So it is very important to try to combat this and making sure that the software and the neural network is correctly identifying objects and images. And now another application is researchers are trying to actually look at these convolutional neural networks and actually make them more complex by taking the same steps that I had previously mentioned of pooling and the convolution, and using further steps of more mathematical operations and linear algebra to make the dense networks more complex and cause there to be less room for possible patterns to be repeated and the image to have its own uniqueness and be able to classify them more successfully. And so this is just some works cited for the images and some of the information used. A lot of them come from other researchers' journals. And so quick synopsis, the artificial neural networks are being applied to the deep learning field to help in image classifications, and there are lots of applications to this to the real world, and such as autonomous driving and the forensics community. Thank you so much for